the quantum gases today. Namely Fermi and Bose. We will do this by first calculating the grand partition function. And this is for these are free particles. So the state is described by occupation numbers. That is, we take the energy spectrum and cut it into cells. And the states inside it is G1, G2, and have N1, N2 in here. Each one of these has G1 states, and then the N1 particles in here, just we discussed last time. And this set is the denominator N, which is just a shorthand for N1, N2, and so forth. And since they're N particles, the summation of N of all I is equal to N. We have to do this because recall how you specify a state for a classical gas. There are N particles, you just state the momentum of each gas, of each particle. But here, there's no meaning for the first particle, second particle. They are all identical. You cannot say that the first particle has one in P1, second one in P2. All you can say is that there are so many momenta, P1, P2, P3, among N particles. So you must have grouped them into cells and say there are so many particles in the first cell, the second cell, and so forth. We group them so that there are many, many levels in one cell in order to do statistics. Then with the energy is labeled by this quantum number, the occupation numbers, and it is of course equal to summation epsilon I times Ni sum of all I. So these are the energy eigenvalues, and the partition function for N particles is the trace of e to the minus beta Hamiltonian, which is equal to the sum over all states of e to the minus En, the energy of the nth eigenstate, sum over all the eigenstates. And this translates into sum over the set of all n, e to the minus beta summation epsilon I Ni. Notice that the n is specified by the fact that there's a condition here. The condition is sum of all n, I is equal to n. That's a constraint on the sum, and this gives you this n. T is beta 1 over kt, and V is contained in the fact that the quantum mechanical levels are defined in a box of size L, and V is L cubed. So you know where the variables come from. Of course, you can write this as summation n, Ni over n, the product of all I of e to the beta epsilon I Ni. So you would think that this is very simple because I have a product of factors, each one is n1, and there's a sum of n1 for each product. But that is not so because of this constraint. These n's are not independent. So at this point, you're stuck. You cannot go on. You cannot calculate this. So you're stuck. So we complete the grand partition function. The grand partition function Q of Z, V, and T. Now n is no longer a fixed variable, it's sum over, so it's going to sum over all n, z to the n power, this is Fugazi, some Qn of V and T. And now I can write this as sum over n into infinity, and I write the Q, sum over n, subject to condition summation ni equal to n times z. Instead of n, I write z to the summation of ni, because ni is equal to n, times the product of I e to the beta epsilon I. Of course, this can be written as product of I z to the z to the ni times beta e to the I. But now, look the advantage of this ensemble. What is the sum? This is that you sum all sets n such that it sums up to n. But then you sum all n here. So this whole thing is going to be the sum of all n with no restriction, no constraint. So once you do this, all the n's are independent. So you can really rewrite this as product over I sum over ni times z to the ni e to the beta epsilon 1 ni. This is an ni here. You have z to the ni, this raised to the ni power. And the ni just sum independently. And ni is equal to 0, 1, 2, and so forth for Bose, and 0, 1 for Fermi. So it's very simple. So we can calculate this. So is this equal to product of I? Let's first do the case of Fermi. It's very simple. Each ni goes from 0 to 1. So it's just 1 plus z e to the beta epsilon I. This is Fermi. For Bose, I sum from 1 to infinity, therefore it's 1 over 1 minus z e to the beta epsilon I. This is for Bose. So we have the answer. And what we need is the logarithm of this to get the equation of state. So log of q z vt is equal to the log of a product is the sum of the log. So I get sum over I log 1 plus z is a beta epsilon I. This is for Fermi. And I have minus log of 1 minus z e to the beta epsilon I. And this is for Bose. And when I have this, I have thermodynamics, because this is equal to PV over KT. With the equation of state, and also, let me write it another way. P over KT is 1 over V log Q of Z V and T, and N over V is equal to 1 over V Z d dz of log Q Z Vt. You take, this is a parametric equation for the equation of state. And if you eliminate Z, using the second equation, you get the equation of state in terms of the density. So now we have the equation of state for the Fermi gases, for Fermi and Bose gases. If you recall that we derived this, we treated this quantum gases in the microcanonical ensemble before. In that treatment, we calculated the entropy, and from that we find that entropy was a sum over occupation numbers, and we maximized that with respect to occupation numbers, and we found the average occupation number, which is the famous Fermi in both distribution. From here, how can we get that from this approach? Well, we get it by just computing the ensemble average of the equation number. That is, in this approach, you would say that nk average is just equal to 1 over grand partition function times summation n from 0 to infinity z to the n times summation n times nk e to the minus beta summation nk epsilon k, and this, of course, is with the constraint prime here. This is the definition. Here's the sum over the, here's the average over the canonical ensemble, and then we average over, we sum over n to get the grand canonical ensemble. And of course, this is equal to minus 1 over beta d by d epsilon k of log q. Because if you differentiate between epsilon k, you pull down an nk. And that's why you have this formula. This is minus beta. And since we have log q already over there, I can just differentiate and get nk. And from this, we get nk is equal to the usual formula, 1 over z e to the beta epsilon k plus or minus 1. With the, you can be minus plus 1. Minus for Fermi, and the plus for both. And this is the famous answer. And z, of course, the fugacity is e to the minus beta mu, where mu is the chemical potential. So we have recovered our previous results. And you will note that for the Bose case, from now on we can, sometimes I'll just write without this bracket, because just say writing nk is equal to 1 over z e to the beta epsilon k minus 1. Because this minus sign here, z must be less than 1. Because otherwise, nk will be negative for some k. So for the Bose case, z is limited to z less than 1. We can approach limit 1, and we'll see what happens at that limit. But for Fermi case, z can go to infinity. So now, to go further, let us now work out the equation of state a little bit further in more detail. I have the equation of state there, logarithm q. We have q, so let's just plug it in and work it out. Let us give an example. For example, if P over KT is equal to 1 over V log of 1 plus Z e to the minus beta epsilon K, it's called a Fermi case. sum over k. And in the thermodynamic, when V goes to infinity, this sum over k goes to V over 2 pi cube integral d3k. But since the integrand depends on the magnitude of k, this also goes into V over 2 pi cube times 4 pi times integral 0 to infinity dk over k squared. Now this V cancels this V, and you have an integral. You have 2, 1 over 2 pi squared, integral 0 to infinity dk k squared log of 1 plus z e to the minus beta h bar squared k squared over 2m. This integral is a transcendental function that you cannot do, so you call it a function. You call it something. You define a function. What you can do is you expand this in power series. In Z. If you can, then you can each term you can do, because each term is a Gaussian. So you can do each term in the power series expansion. And each term gives you a very simple formula. So in fact, you get what is this? You get what this is known as 1 over lambda cube f 5/2 of z. The function f 5/2 is obtained from this integral. And you will know how f 5/2 of z is equal to z minus z divided by 2 to the 5/2 plus z squared to the 5, z cubed times 3 to the 5/2 minus z fourth times 4 to the 5/2 and so forth. And this is called f 5/2. So that once you define that function, the equation is related p over kt is equal to 1 over lambda cube. Lambda cube is a thermal wavelength. 2 pi h bar squared mkt into the square root times f 5/2 of z. And then n, the density is 1 over lambda cube. Z d dz gives you f 3/2 of z. And this 3/2 of z is defined the same, except this 5/2 is replaced by 3/2. So that's the equation, parametric equation for Fermi. If we do it for both, you can repeat the same thing. You get 1 over lambda cube. It's called g 5/2 of z. And here you get 1 over lambda cube, g 3/2 of z. And g is the same as f, except that it is not alternating. The g is equal to, you change all the signs to plus. So it's very simple. So this is our result. It's very nice. The equation state is expressed in terms of some function f 5/2 and then g 5/2 and so on. And f and g are defined very simply. The coefficients is 2 to the 5/2 and so forth, but except in the Fermi case it's alternating. And so everything about these gases depend on the properties of this function f and g. They are not elementary functions. We have the power series, so we can find expansions. For small z is this. For large z, we can find expansions. What you can do is express that in terms of a integral representation, and then you can discuss the high z behavior and so forth. So from here on, I will discuss the Fermi case and the Bose case separately by relying on the special properties of these functions f and g for each case. And this is a non-stop derivation. I hope that you appreciate the simplicity of this derivation. There are some indistributions, but the logic is very simple. You just calculate it, and you get a very beautiful result in the end. So now let us discuss the details with emphasis on the physics. So first, I would like to discuss the Fermi gas. I think maybe you can appreciate too that it is much simpler to compute in the grand canonical ensemble. You just do integrals instead of stopping and count things. Doing integrals is much easier than counting. Nk is 1 over e to the beta epsilon k minus mu plus 1. We have to find out how mu behaves as a function of temperature and density. First, let us discuss low temperature, absolute zero. You see that e to the beta epsilon k minus mu, when beta approaches infinity, what does it do? If this is positive, this goes to infinity. If this is negative, it goes to 0. So it's either infinity or 0. If epsilon is greater than mu, if epsilon k is less than mu. And therefore, at absolute 0, nk, if you apply the function epsilon k, is either 1 or 0. It's 1 up to some, it's 1 and then up to some, after when the energy is greater than some number EF, it goes to 0. And this is very simple. It just means that if the epsilon k, which is, the k as a function of k, which of course because the h bar squared k squared over 2m, you have a hyperbola like this. This just means that all the states up to some epsilon k, epsilon EF are occupied, and all the others are empty. This is a Pauli principle. Each level holds one particle. Now, if the particle had spin, each spin would count as separate Fermi gas. So each level would hold 2 particles. So each level holds at most 2s plus 1 particles. S is the spin. For electron, each level holds 2 particles. And epsilon F is called a Fermi energy. Epsilon F. It is also equal to h bar squared kf squared over 2m. And kf is a Fermi momentum, or h bar kf is a Fermi momentum. That is h bar kf is equal to Fermi momentum. And also, if I put EF is equal to K Boltzmann TF, then TF is the Fermi temperature. So if I have n particles, say spin 0, then they all fill up to some level EF. How do you determine EF? You determine it by requiring that the sum over n and nk be equal to n. So let's do that. N is equal to sum of all k of nk. Oh, of 1 actually at absolute 0, with k smaller than kf. But if this is for one state, the k labels the single particle state. If the speckle has spin, you have to multiply by 2s plus 1. Because there are 2s plus 1 states with the same energy. S is spin. And this is equal to 2s plus 1. This sum becomes v over 2 pi cubed times 4 pi. In fact, it's just 4 pi over 3 kf cubed, right? Because this is just a sphere in k space of radius kf. So this gives you n over v is equal to 2s plus 1 divided by kf cubed over 6 pi squared. And kf, therefore, is equal to 6 pi squared times the density divided by 2s plus 1 to the 1/3 power. And therefore, the Fermi energy, which is equal to h bar squared kf squared over 2m, is equal to h bar squared over 2m times 6 pi squared times the density divided by 2s plus 1 to the 2/3 power. So this is the Fermi level. And it depends on the density of the system and the mass of the particle. That, of course, is a very important quantity. So to get a feeling, let us make a list for the different systems. So electrons in metal. The density in unit Cm minus 3 is about 10 to the 22. And EF is about 5 electron volts. And the TF is about 10 to the 4th degrees Kelvin. It's very high. In a nucleus, for an atomic nucleus, consists of protons and neutrons forming 2 separate Fermi gases. And they fill up to a certain level. And you use the nuclear mass and the density of a nucleus. And this is 10 to the 44. This turns out to be 10 MeV. And the Fermi is 10 to the 9th. And for electrons in a white dwarf star, in a star, the density is 10 to the 30th. It's 20 MeV. And the temperature is 10 to the 11. The Fermi temperature corresponds to this energy. When this temperature is high, it means that high compared to room temperature, it means that it's very hard to excite these particles. So even at room temperature, this is a pretty good distribution. Now let us calculate the internal energy at absolute zero. And the pressure. You can calculate the internal energy either from the grand partition function or just by saying that U0 is equal to summation of epsilon k times the occupation number such that k is less than kf. This was spin 0. If this spin, you put 2s plus 1, so that's just so bit. And this is equal to v over 2 pi cubed times 4 pi times integral dk k squared h bar squared k squared over 2m 0 to kf. That of course can be easily done. You just do the algebra and you find that this is equal to v over 2 pi cubed h bar squared over 2m times 4 pi over 5 times kf to the 5th power. On the other hand, we already know that n is equal to v over 2 pi cubed 4 pi over 3 kf cubed. Therefore, if we divide one by the other, the energy density, the energy per particle at absolute zero, turns out to be 3/5 h squared kf squared over 2m, or it's 3/5 of the Fermi energy. This was spin 0. So the internal energy is not 0, but it's 3/5 times that of the Fermi energy. Now this is the energy at absolute zero. So if I differentiate it relative to v, I get the pressure. The pressure at 0 is going to minus du dv. This is pressure at absolute zero. And I get 2/5 n times epsilon f. That's a very important number. You see, at absolute zero, the pressure is not 0. You need a container to contain those fermions, because those fermions, they cannot be at rest. They stack up so that they have to move. And when they move, they impinge against the walls. And if there's no walls, they'll just all fly away. So there's a 0-point pressure. You need a container to contain this gas. And for a metal, for electron, P0 is about 10 to the 4th atmosphere. And this means that the ionic bonds in the metal has to be strong enough to hold it. And that's not too high. But you take a white dwarf star P0 becomes 10 to the 53 atmosphere. It's an enormous pressure. And in a white dwarf star, it is held up by gravity. And they fight against each other. And later we'll see that the gravity is too high, the star collapses. The gravitational collapse. And what prevents collapse is this Fermi pressure. So like a white star is a special case in which the star inside is only electrons and helium. And in that case, the star is prevented from collapsing because of this Fermi pressure of the electrons. So this is the absolute zero. Now let us look at the case of low temperature, not zero, but low temperature. We're still discussing the Fermi case. Low temperature. T much less than Tf, but not equal to 0. What happens in this case? Nk, it looks like this is absolute 0. 1. This is a T equal to 0. For T not equal to 0, but much less than Tf, only those electrons near this Fermi level are affected. They get excited from below the level to above the level. So this looks like this. It becomes like this. This is T greater than 0, but T much less than the Fermi temperature. Of course, if it gets excited too much, it'll become this like this, and that looks like Maxwell-Boltzmann. And this width is of the order of kBT, because kBT is the thermal energy. And that's the energy you need to excite this layer of electrons from below the Fermi surface to above the Fermi surface. So then qualitatively, UT minus U at 0 estimate is of the order of kT times the number of particles excited. That's the number of particles taken from below the Fermi level to above the Fermi level, leaving the holes behind. And this we can estimate to be the total number, a fraction of this, and that fraction must be T over Tf. So when you put this together, this is of the order of k T squared over Tf times n. The coefficient in front, of course, is not exactly determined, but this is the general dependence on K and N, on T and N. And therefore the heat capacity, Cv, is then of the order of N K T over Tf. That is, Cv over Nk is of the order of T over Tf. If you plot this, it's linear. And then you know that at very high temperatures, if it goes classical, it goes to 3/2 classical. But at low temperatures, it's linear. That is a very important point. You see, Boltzmann was faced with a paradox. Boltzmann thought that in Boltzmann's time, people thought that the heat capacity is always 3/2 because, equipartition, 1/2 kT for per degree of freedom. So they wonder, if there's so many electrons in the metal, how come we don't see them? They don't contribute to the heat capacity at room temperature, because room temperature is 300 degrees, but the Fermi temperature is 10 to the 4th degree. So at room temperature, the electrons in the metal is as if they were at absolute zero. The heat capacity is linear, it's very small, it's linear. Whereas classically, they should be 3/2. So according to classical thinking, you are missing a lot of internal energy. And that was a puzzle. And that was solved by quantum mechanics. Namely, that those degrees of freedom that are not excited do not contribute to the thermodynamics of the system. So that from the point of view of heat, the electrons are frozen at room temperature. Now, if you want to calculate the coefficients more precisely, you will have to solve for the chemical potential. A quantitative calculation must start with solving lambda cube n is equal to f 3/2 of z. Find z as function of n and t from this relation. Now, f of 3/2 t looks like this. As function of z. For z near 0, the power series expansion is good, so it just goes linearly like this. But for high z, you have to continue it, and you can show that it bends over, and this goes like log z to some power. Log z to the 2/3 power. So this is the way it behaves. So at log z, it goes to infinity, very slowly, logarithmically, and it goes 0. You can see from here that lambda is so this says a 2 pi h bar squared over mkt cube 3/2 times n is equal to f 3/2 of z. You can say that as when t goes to infinity, this is small, then z must go to 0. So for high t, the power series expansion is good, and that's the classical limit. For t approaches 0, z approaches infinity, because t goes to this is go to infinity, and this is a quantum limit. And the classical limit is very simple. You just take the high t limit. It's very simple because you just take the power series and keep the first term. So high t you have lambda cube n is roughly equal to z. You just keep the first term in the power series expansion. But you also know, but P over KT is equal to 1 over lambda Q F 5/2 of Z, which is also equal to Z because in the first term doesn't matter, but it's 3/2 and 5/2, so it's just equal to Z over lambda Q. So when you put these two together, you get P over KT is equal to N, which is a classical equation of state. So you get back the Boltzmann, the Maxwell-Boltzmann result. For the low temperature case, you have to work a little harder. You will have to use the expansion, and you have to use F 3/2 of Z approaches as Z approaches infinity. The result is 4 over 2 square root of pi log Z to the 3/2 power, 3/2. And this, of course, is equal to n lambda q. And then you can find C, and you got everything else, and you get. I'll just quote the results. You get U over N is equal to let's say first mu. Mu. You know that is epsilon f at absolute 0. This gives you a correction. The correction is 1 minus pi squared over 12 T over Tf squared plus, so this is expansion T over Tf. And U over N is equal to 3/5 epsilon f. Again, it's 1 plus 5 pi squared over 12 T over Tf squared. And the pressure is equal to 2/5 n epsilon f times 1 plus or just differential. I'm not going to quote it. Just from this you can work out all the rest. So anyway, you can see how you can work out the next correction. There are a lot of applications of the Fermi gas. So let me just talk about it qualitatively. I'll go a little bit over the time here because I do want to go for qualitatively the kind of application you can make use of for the Fermi gas. And these are physically very interesting and very important. So I will go over this. I will take the time from the next session. First is semiconductors, of course. That's very important because that's where the computer chip industry is based. This depends on the fact that the spectrum, let me do it, epsilon k over k of an electron in the metal, it's not a parabola. But because the crystal has a periodic structure, band gaps open up. This band gap in which there are no levels. And that's something that you probably know because the electrons go through the crystal and they get reflected by the crystal size. And when they reflect at certain K, they reinforce each other. At certain K, they cancel, leaving these band gaps. And this is called the valence band. And this is called the conduction band. Now, I'm sure you know all this, but I'll just say it in words, so I don't make us write it down. If the valence band is completely filled, then to excite an electron, you need to go through the band gap. It's a high gap. So the thing is an insulator. It does not conduct. But if the valence band is not completely full, then electrons can freely go up and down in that band, and you get a conductor. However, a metal is never pure. They're impurities. And those impurities contribute levels. They have levels up here, in here. These are impurity levels. So suppose this band is completely filled. It can excite things up to it, but it excites things to these impurity levels. And that's a semiconductor. And this is called an acceptor level. It accepts electron. And if this is filled, it could put electrons into the conduction band and those to the donor levels. And from this, the whole industry goes up. And the whole electronics goes up. So I'll just leave it there. So that's the entire computer industry. The second electrons in external magnetic field. And these are called Landau levels. The spectrum in the beginning is like this. It's a continuum, the energy. This for no field, B equal to 0. But for B greater than 0, electrons would go around in orbits around this. And these fields would bunch up. All these bunch up in the one level, all these bunch up in the second level, equally spaced. And this is called Landau levels. They have a spacing. And more important, each level is highly degenerate. Many levels bunch into one, and this spacing is EH bar MC times B, and the degeneracy of the levels is equal to EB over H bar C times A, where A is the area. There's electrons going around in an area A, which is macroscopic. This is because this field being uniform, the center could be anywhere in this area, and the energy is the same. So the degeneracy proportional to A, and A is macroscopic. But this has some very interesting manifestations. First, it gives you diamagnetism, which I'll just leave it there. You can calculate the diamagnetic susceptibility from this. Whereas classically you cannot. Classically you get 0. Here you get it because of this gap, of the 0-point gap here. It's not 0. So that's an important application. Second, you get the Haas van Alphen effect. That's very interesting. It means that the susceptibility as function of B, as B decreases, it oscillates like this, and here is the cycle. Why is that? Because imagine this level is filled to G, it's all filled. Now we suddenly decrease the magnetic field, the density goes down. So some electrons are forced to go up. And that's a violent process that makes it oscillate. The B keeps decreasing, the electrons keep having the force going up. And this makes the susceptibility oscillate like this. And at this point, it's with an infinite frequency, theoretically. And 3 is a quantum Hall effect. I cannot talk about it, except this is about electrons in a two-dimensional ribbon. And you apply a magnetic field. And depending on whether this is completely filled or not filled, very interesting things happen. In particular, if this is half filled, the electrons behave very strangely. They look like fractional charges and so forth. And we haven't seen the end of it. And the hardest thing in condensed matter physics now, coming from this, are those so-called topological insulators. It originates in the study of quantum Hall effect. In the past 10 years, it has seen 2 Nobel Prizes in this, the integer and the fractional quantum Hall effect. In particular, it's a contribution of Cui-Qi, fractional quantum, and the topological insulators do the Wen Xiaogang and Zhang Shoucheng. And the final application I want to mention is a white dwarf star. A white dwarf. It's a star that is very old. It has burned up all its helium, all its hydrogen fuel. It's all helium now. So if a star, there's only helium and electron. The helium produces the mass, so it likes to collapse the star. The electrons tries to push out with a Pauli pressure. The helium tries to collapse the star, and these two fight against each other. Depending on the mass, the balance shifts towards one or the other depending on the mass. And if the mass is greater than m subcritical, the star collapses. And this mc is about 1.4 times mass of the sun. That's called the Chandrasekhar limit. This is a very interesting pure number. This pure number is a combination of Planck's constant, the velocity of light, the gravitational constant, and the actual mass of the sun. And so Chandrasekhar shows you how the high star collapses, and the endpoint is a neutron star. And this is Chandrasekhar. And then Volkov and Oppenheimer show that if the neutron star is massive enough, it collapses to a black hole. And then Snyder and Oppenheimer shows you how this black hole collapses into nothing. And that last calculation is very interesting. That was done in the 30s. They show in a simplified model that a black hole, if it's massive enough, to be a, if you notice mass number to be a black hole, it collapses, and the radius of the black hole as a function of time is periodic. It's a cycloid. You know what a cycloid is? It's you have a bicycle wheel going on. A point on the wheel would trace out a cycloid in space. So it's very interesting. They show that the black hole collapses, but there's a rebirth. It expands again and collapses. It's very beautiful. It's exact calculation. And this makes some people think that maybe we live in a black hole, and that we are in the expanding phase. We're here. Eventually, we'll come back and collapse, and then there'll be rebirth and so forth. But that's only a model. So we'll take a rest and we'll talk about the Bose gas.